think so. All right, let's see what happens. Oh, I should hit the chat. Yeah, okay, all right. So it's always, I need someone to collapse the wave function to let us know that we exist. I'm here. James knows he's here, but do
I
we
feel like I'm
really
here.
exist if somebody doesn't observe us? How do you feel on that, James? Do we exist if somebody doesn't observe us?
The tree falling in the woods kind of thing.
Yeah. Does existence require an observer? Let's just start with the greater anthropic theory, just as the entrance to this conversation.
Yeah, if an astronomer stays on mute on Zoom, was he ever even on the call?
How how much do you hate Zoom? I I used to think that I was like, look at this wondrous technology that we've got that I can share with people so that they can just press one button and show up and do an interview, and it's just made, I don't have to set them up on Skype. And I even have a sign that I hold up that explains to people how to unmute their.
Oh, that's funny. My wife just bought me these, like, I think they're for students. Just bought me these flashcards, so
Yeah.
so you can. There's like a, where is it?
Oh, like the Zoom flashcards?
They're like Zoom flashcards. I think they're meant for students, but she was like, maybe these would be useful for you, and I think that's hilarious. Yeah. So there's the
That's so good.
I need that actually every day. So this pile of flashcards turned out to be very, very useful. So I don't know. Do I hate Zoom?
Yeah.
I guess my biggest disappointment is that after a year of this, after a year of living in my basement and having my kids stomp around upstairs, bless their hearts, that we haven't improved this. Like we've had a year.
Yeah.
That's an eon in the tech world. Yeah. How are we still how is this the best I know.
Where's the hall guy? We should be sitting in a virtual room, seeing each other. All of the viewers should be in this virtual room, sitting in one easy chair, part of the conversation.
A big virtual beach, like in virtual Hawaii. Yeah. That would be perfect.
Yeah, that would be perfect. We've had these conversations in the real Hawaii, and so we know what can be achieved, and we're just not there yet. Hey, who are you? What do you do?
I am me. My name is Jim Davenport. I'm a research professor at the University of Washington, and I'm the associate director of the Dirac Institute. I'm wearing the hoodie, so we get the free promo there. Dirac, there you go.
Nice.
It's the research institute which brings together people who are interested in big data and algorithms and the frontiers of time domain science throughout astronomy. And so that's one of our big teams at the University of Washington. And so I'm the associate director, which is a big blessing. To be able to help the people. And that's what a big part of my job is, keeping the lights on and keeping the people working, I hope.
And we live in roughly the same part of the world. I'm just across the border from you in the seething COVID hotspot that is Canada right now.
Yeah, Cascadia, yeah.
Yeah, I live in the Cascadia, yeah. We share a devastating subduction zone.
Yes, I was actually going to ask you if it's like dumping rain on you, because it was beautiful yesterday here. Yeah. So I'm in Edmonds, Washington, which is just north of Seattle.
Yeah, I'm on Vancouver Island.
It is miserable today.
We've got hail, actually, big awful hail clouds right now.
Okay, you win.
Yeah.
We're just getting rain.
Yeah. It's a pretty weird thing. We only get it in like March, but then my wife is from Texas, and so she looks at our hail and just laughs at us. Come on, that's ridiculous. Like, hail should be the size of your fist.
Golf ball minimum.
Yeah, golf ball, exactly. If it can't tear your car apart, down to the nuts and bolts, and it's really just not hail. Cool. So, all right. Were you born and raised in the Northwest, or did you?
I'm born in Virginia, but spent most of my life in the Northwest. Yeah. So I actually went to college here at the University of Washington.
Oh, great. Okay.
Went to California for a few years, came back for graduate school, went up to Bellingham for a few years, so even closer to you actually, and then came back for a research position that I've managed to wiggle my way into a research professor position, and I'm just clawing my way up, trying to build a life,
Yeah, well, I mean, you do a great job, I think, of balancing between active research. I just checked your Google Scholar list, and you've got a ton of papers that you're producing, a part of like a couple a month 3 a month. I've been, there's a big list there. So, I'm not sure we'll be able to cover all of it. But at the same time, I think you do some of the best coverage of the work that's happening at these professional astronomy meetings for other astronomers and the general public at the same time. So, and parent and, person trying to avoid rain all the time. How do you keep that all balanced?
Poorly, I think is the answer, especially in the last year. About 4 years ago, I started doing this video project, doing this vlog. I had been turned on to this idea of vlogging by my brother-in-law, who's a music producer, and I just was loving what he was doing and showing his process. And I think one of the things that excites me about astronomy and about art and technology, and the theme I find that weaves through all things that interest me, cooking, is I love the process of creating things. And so I was really entranced by watching him like sit in his studio and like go from nothing to music and, interview other musicians. And I was like, I love being a fly on this wall. That's really fun. And so it started as just sort of an idea, like, what if I took a camera and went to an astronomy meeting and just showed that process, tried to capture what it's like? Because for me, the meetings, even though they take a lot of time and they're exhausting, they're also a source of big inspiration and big sort of idea generation. I go to this, we call it the AAS meeting, the American Astronomical Society meeting. I go almost every year because it's part of my practice of like generating ideas and catching up with what's going on in my field and my friends in the field. And there's those moments, there's these magic moments where you're sitting in the audience and you're writing notes or you're scratching your beard if you have one. And you have that light turn on, right? You have that moment of like creation in your mind where an idea didn't exist and then it did. And it's like a wild thing. It's like that adrenaline rush where you're like, oh my goodness, we could do this thing. Or I've never thought of that before. It's that amazing spark. And I wanted to capture that. That was my goal. Bring the camera, film everything, try to document the experience and see if I could capture the moment of like idea creation. And I think I failed at that because it turns out that's impossible to actually watch the light turn on in your head, I think.
Right. You like make a note of that in the video. Like, this is the exact moment.
Yeah.
Like, you could just like slow-mo in your face as you're suddenly discovering something interesting.
It probably looks ridiculous too. And for me, it's probably like I'm sitting here staring literally at the wall and then I go, huh. And then I just start working. Like, it's probably very boring to actually see. Yeah. But it turned out to actually be a really fun project to get to document what it's like, because it is a unique experience that I take for granted after having done it for 15 years.
Mm-hmm. Yep.
Going to these meetings and being around these brilliant people and seeing the excitement, seeing the ideas fly through the air. It's really exciting.
Yeah, so, they're exhausting and they're wonderful. I mean, I've been to probably 4 or 5 of them at this point, and my job is to be the fly on the wall. No one asks me to participate at all, but that allows me to just check in with people, ask them a bunch of stupid questions, find out what they're working on, and sometimes even act like glue between people, because sometimes I'll be like, oh, did you hear about this work that so-and-so's working on over here? And they're like, no, I did not. That's really interesting. But that's what it's about, really, is that chance to collaborate in person with people to shorten this process, of this back and forth of like, oh, I wonder who's working on this. You look at the researchers, who's working on this. You make these connections, but you can just be at a party and there's a lot of parties, and someone can just say, oh, you work on this, you work on this. They connect you together and you have a fascinating conversation. It's just this beautiful kind of investment in chaos that you just don't get a chance to do. And I think, these kinds of professional meetings for a lot of people who are starting in this field of astronomy or even the sciences in general, they don't get a chance. They don't see that part of it until they're a little further on in their career, that their department is willing to spend some money to drag them along as a postdoc or as a doctorate candidate or whatever. And your videos, I hope, give people a chance to see, just to give them a sneak preview of what that life is going to be like for them as they're getting prepared to into this career.
One of the most enriching things about the project has been how many students, like junior level undergraduates or introductory grad students, who have come up to me in the last 3 years at these meetings and said, I watched your video on 10 tips to prepare for the meeting, or I loved that video where you showed the hack day where you guys worked on projects together. And I'm like, yes, I am reaching this. I mean, it's not a huge audience. There's not that many astronomers in the world. but we call that like in-reach. There's outreach.
Yep.
Outreach is, I think we're doing right now. We're talking about science to the world.
Yeah.
I think that's an important part of being a scientist.
Yeah, none of those astronomers are going to watch this conversation. They're busy.
But the in-reach of like having something that's speaking to, I mean, I have a vibrant group of students that I'm working with and a bunch of collaborators, but that's probably like 50 people.
Yeah.
You know, like it's not that many people that you can affect and that you can mentor and share and support. And being able to find a medium that allows me to talk to other scientists, especially the junior ones, especially the ones in other countries or at other universities that don't have access to the resources that we do. We're a huge university. That's I think a hidden treasure that I stumbled into, and I've really enjoyed.
Yeah, I think I
miss the meetings. Too.
Yeah, I think you're doing a fantastic job. Yeah, it's true. I do miss the meetings. I after every meeting, I'm like, okay, that's it. That's the last one. I'm not going to do any more of these. The travel, the cold afterwards, and then I come back and I go, oh, the next one sounds. Oh, it's in Hawaii. Sure, why not? I've always wanted.
One more.
Yeah, one more. So let's talk about your research. So what do you actually, as your day job, when you're not teaching and when you're not YouTubing, what are you researching?
Yeah, my number one research program for the last 10 years has been studying stars. So I think you put it in the description of the video, time domain astronomy. And that just means watching how things change over time. In astronomy, typically this means watching the brightness of things change. So we've got telescopes in space that are staring at stars, or we've got telescopes on the ground that repeatedly take pictures of stars. We're measuring the brightness of those things. So it looks kind of like a stock ticker. You're watching the brightness go up and down. It turns out a lot of the algorithms that you would use to study stocks over time or things like this turn out to be really interesting. And we borrow from that field pretty liberally. And I think some of it even works its way back into that field, which is kind of cool.
Well, often, it's a good career training, right? Most quants are just astrophysicists that
wanted to have a stable job.
Yeah, they wanted a paycheck. Yeah.
And we have a lot of people that take these kinds of big algorithm theses and go into data science, go into work for big tech companies. I think it's a really great connection. So my research is focused on data from the Kepler telescope, may it rest in peace. Right now, the TESS telescope, and also the Zwicky transient facility, and hopefully someday soon, the LSST survey on the Vera Rubin Observatory. So hopefully we're seeing first light there in the next year and a half, something like that.
Yeah, so now the people who are watching this channel know that I just really won't shut up about the Vera Rubin Observatory and the LSST. And I think, maybe it's coming from my computer science mindset, the idea of digesting just enormous databases and looking for numbers that are different feels like a very productive way to do some really interesting astronomy. So can we just talk a bit about what will Vera Rubin accomplish in this field? What does this really bring to the table? How is this going to change things?
So as it's advertised, the Vera Rubin Observatory during the LSST project, it'll last 10 years, and it'll do a map of the sky. It'll take a mosaic picture of the sky roughly every 3 days. So every night it'll take about 1/3 of the sky, and it'll snap pictures. The field of view is 100 square degrees or something like that. So it's a big mosaic of the sky, and it just takes a big still picture of the sky every night, and it stitches those together. And that's kind of a classical astronomy thing to do. Take a lot of pictures of the sky, stitch them together. Where the magic happens is both doing that over 10 years and with a 8-meter telescope. So it's a humongous telescope. You're seeing really faint objects. So it's a massive survey.
Same size telescope as each of the very large telescopes as the Gemini Observatory. These are monster telescopes.
This is a monstrous piece of glass that was made in Arizona. Now it lives in Chile. It's up on the mountain. It's been, I think, mounted into its mirror cell. I think it is put where it is going to live, I think, forever. I hope it doesn't go anywhere else. It's a monstrous piece of glass, and that means it's going to see incredibly faint things. So that's exciting. So you've got an incredibly faint survey over 10 years. And then the magic comes in the computers, as you said. It's the software, it's the algorithms. So one of my mentors said that algorithms are the new observatory, because the ability to look for subtle changes or interesting patterns or interesting connections between things, that is the power that we have now that we didn't have 50 years ago. And so the trick, and I hope where my work is, it's straddling the line of classical astronomy, trying to extract as much understanding as you can from a precious few photons of light, or the little hints of what's going on that nature's giving you, with this wealth of data where you've got we call these light curves, where you've got light curves with thousands of data points over 10 years. How do we infer what's going on in the stars and how they're changing and what that means for life and the evolution of stars from a billion of these things? There's the first pass things like, all right, things are bright, things are blue, things are red. There's the first pass survey, and then you get into the nitty gritty where you have a billion examples of something and you're looking for the one outlier, or you're looking for the weird trend that nobody expected. And that's where I hope my work is going, and that's where I think the field is going.
I mean, it really is the difference between looking at a picture and looking at a video, seeing one frame. I mean, right now there are surveys that have been done that go to the depth that Vera Rubin will be able to capture, but it was like one picture taken laboriously over the course of many months, and not even to the same level of depth. When I think about, say, Pan-STARRS or the Sloan Digital Sky Survey, I mean, they're still not as comprehensive as Vera Rubin.
Rubin is going to go 1,000 times fainter than any of those,
and
which is amazing.
Video. And then at the same time, take that picture every 3 nights. So
that's right.
Yeah.
I think the single image that Vera Rubin Observatory will take is as deep as if you co-added or you combined all the images for a single field of view from the Sloan Digital Sky Survey. I think that's roughly about the same. So that's what you get from a huge piece of glass, is you get to see really faint. Yeah. Now there is like a funny problem here, which is when you're roughly the biggest survey in town, there's a few bigger telescopes, but you're roughly the biggest telescope around, and you discover something really interesting and faint, nobody else can observe it. Is like there's actually a problem here in that we don't have a 30-meter telescope sitting by waiting to follow up these other things. And so I think a lot of us are hopeful that not only will the LSST project be this huge discoverer of science and this huge opportunity for people at all universities around the world to discover things, but it also will motivate that next generation of telescope, those space telescopes that we can't afford or we won't build right now, those massive
October 31st. James Webb is going to fly. It's going to fly.
Yeah, fingers crossed, fingers and toes crossed, all of it, yes. Yeah. But there's a funny thing when you have something that's 1,000 times fainter than your best telescope can reasonably observe. How are we going to learn more about these things? So that, the work never ends. That we always have to be looking. Even we're getting ready for first light with LSST and the Vera Rubin Observatory. We have to be thinking about what's the next thing we're going to build, because these things take 30 years to build sometimes.
So that's interesting to me that Vera Rubin is going to be, for example, finding, let's say, Planet 9. And it's going to be like, here you go. Here's a nice time set of images of an object which is clearly large and in the outer solar system, moving in exactly the right orbit. And go ahead, astronomers. It's up to you now. And they're like, we can't see it. Like there's like maybe we can get some Hubble time for a year and try to observe this thing. But
you can guarantee that, somebody, if they find it, somebody will point Webb at it if they can.
Of course. Webb,
right? Like
Webb,
you'll go after it as much as you can.
But
and it's unfair to say that nobody can follow up things that LSST and Rubin can see. It's just that it becomes extremely expensive. You have to sit on it for hours with like Keck or one of the biggest telescopes in the world.
Yeah.
So there's a handful of things, but you have to be super certain, right? You can't do, we have these telescopes that are like 3 or 4 meters, which when you stand next to them are like terrifyingly large, but then you think about, well, this is still 100 times smaller than the other telescope that I'm talking about. But these telescopes, we have a lot of them. And so you can get, as a student or as a junior faculty member, you can get a lot of time on them. So for the bright things, for the things that like TESS discovers or the ZTF survey discovers, for those things, we can get a night or two to just go and hunt and go chase them. We'll be able to chase a very precious few things with LSST, but we'll have to be very certain that they're super duper interesting. And so this is, again, where the algorithms come in. They're going to say, okay, this was cool, but was it a 1 in a million object that's worth going after and spending an entire night of Keck time on? Maybe. And so you have to be really sure.
And you talked about that next class of telescopes coming. You've got the Magellan, the Giant Magellan telescope. You've got potentially the 30-meter telescope, wherever it ends up being. You've got the extremely large telescope that's coming in 2026. You've got James Webb. You've got, but that's kind of it. And then Hubble still is going to work hard to keep up. But
I had heard of the overwhelmingly large, like the OL, was it?
Yeah, the
overwhelmingly large telescope.
Yeah, 100 meters. But which they canceled it because the budget was going to cost $1 billion.
Yeah.
And they said that's too much money. We can't spend that much money on a telescope. Although I think that's extremely large telescope is going to be $1 billion, 1.1 billion euros. So it's roughly expensive.
James Webb has cost a lot.
Yeah.
Whatever it is.
Yeah, all of it. Just all the money and whatever you had to spare. So I mean that idea, I mean, like, it's going to be dumping petabytes of data. Like if you are a Hadoop programmer and have a lot of Amazon resources available to you, you can just like go crazy processing.
I think that's right.
That nobody can ever follow up, which is
but people can always go check your work, right? Because the data will be there. You can always go back and check the work.
Yeah.
You can always. I think that's where the big opportunity is. I mean, we talk a lot about democratizing science, which I think is kind of an intriguing but loaded term. One of the great opportunities with this survey is that the data is immediately public, with some asterisks around like where we send the data internationally and whatever. But roughly speaking, the data is immediately public to everyone, especially everyone in the U.S.
Yeah.
Because the U.S. tax dollars paid for a large chunk of the telescope. And that's also a revolutionary thing. The data will come out within a few minutes. There will be alerts. So if there's a big supernova or an object that's changed or moved, the software will trigger an alert and publish that within 60 seconds. So if you are looking for a very rare class of thing that goes bump in the night, within 60 seconds you'll have a trigger, and you can point your other telescope at it, space telescope at it, whatever. And you can go after it. So those are really special things, and those are open to everyone. And I think that's really unique. So there's a lot of opportunity if you're at a smaller school, if you're an amateur, if you're just an enthusiast astronomers are like myself are learning a lot of computer science, are learning to program. I am also a terrible programmer. If you were to compare me to like a software engineer, like nobody's coming knocking at my door to write the next set of like Netflix algorithms or something. Because I'm a scientist. That's not my specialty. And so we have to balance this need for competency and fluency of being able to speak computer languages and also to be able to be scientists. So I think there's a partnership there.
Yeah.
Not only do we need people with access to Amazon's web services, we also need software engineers to come and work with us, to help us develop tools, to help us not reinvent the wheel. There are people who are learning to classify cats versus apples, and we need some of that technology and don't need to reinvent it ourselves.
Yeah, it's interesting. I think that, if there was some very motivated computer science people who knew quite a bit about astronomy, they could start digging through the Vera Rubin data and pull together some mind-bending discoveries that could then be channeled up, into the hands of astronomers who could do some follow-up observations. What are some hints that the universe is doing that we're not, like when we're not looking, that you are hoping will be captured by this sort of whole field of time domain astronomy?
Hints, that's a good question. That's an interesting question. Things that I hope we will discover. I'm really hopeful we're going to discover, I'm internally interested in what the sun looked like as a young star and what the sun looks like as an older star. We only get this one point in time. And there are a lot of hints we get from things like LSST and also things like TESS, these sorts of very precise surveys of stars. With LSST and with Rubin, I really want to know what the youngest stars look like and what the rates of flares are and things that might be really disastrous for early life. We have hints of it from TESS that these young stars flare a ton. And that's very bad if you are a microorganism on the surface of a planet and giant irradiating flares are blasting you constantly, like on things like Proxima Centauri and nearby stars, nearby M dwarfs and things like that. So, being able to study 1 billion of these objects, we're gonna have a good census of what they're like when they're very young.
And would a flaring star brighten up over a time period that would be well caught by Vera Rubin?
Maybe, yeah. The nice thing about things like TESS is because they're looking for exoplanet transits, they just have sort of an unblinking eye. They're staring for days and days and days, and so the flares last hours, 10 hours at like most usually. With Vera Rubin, you're going to get a snapshot. You're going to get like a 30-second picture, and then you're not going to come back for another day or 2 or 3. So you're going to get these outlier points that are like super bright, but you'll get 100 of them or 1,000 of them in a single wide field snapshot. There'll be 1,000 stars that are undergoing this flare behavior, and you'll come back a few nights later and they'll be back down to their baseline. This has the intriguing result of like the faintest stars, and these M dwarfs, which flare a lot, are super faint, will be even fainter than Rubin can see at some point. You know, if they're on the other side of the galaxy, even Vera Rubin Observatory can't see them unless they're flaring, unless they're popping off this flare that brightens them by a factor of 1,000. And then all of a sudden they pop into view, and we call this a transient, something that pops into view for one picture or for a few days in the worst case scenario, and then they're gone. And so they're like these little flashes of light that you'll see, and hopefully, if we observe the sky long enough, you'll see them again, that they'll come back. But we call this sort of the transient fog of this like foreground of M dwarfs that are just like blinking at you, that are very faint stars on the other side of the galaxy, blinking into view every now and then.
And so do you think it's possible that we actually have a bad estimate for the number of M dwarfs that are out there? I mean, just based on, because they're so dim, right? You're just doing a local survey of what you can see nearby.
But yeah, it's true. The furthest M dwarf we've ever seen is like a few tens of thousands of light years away at most. Is that right? Like, it's not that far.
Right.
Like 10,000 light years or something. It's like just really not very far. And that'll go out of, a factor of a few with LSST, but the galaxy is much larger than that. So yeah, it's possible. I really hope not. The thing about M dwarfs is they're faint, but they're super numerous. They make up like 70% of the stars in the galaxy. And so, we hope that the slice of the galaxy that we can see near us is like the rest of the galaxy. We hope we're not in too special of a place. The universe is very troubling if we find out that we're in a special place. This is like the anthropic principle. You hope that our little island of the universe is not unusual compared to the rest of it.
Yeah.
Or else that makes everything else hard.
Yeah, I still like thinking about the discoveries that could be made in the solar system in terms of asteroids, comets, Planet 9, hopefully, even things that maybe interesting things that objects are doing. We might see comets flaring up. We might see, the possibility to see other solar systems, as you say, here in the Milky Way, stars, interesting flares on stars, supernovae, things like that. And then the ability even to see right out to as deep as you can go into the observable universe, the extragalactic universe, looking at supernova happening in other galaxies, and who knows what's out there. And I think that's the thing that I'm most excited about, is every time you get one of these new capable telescopes that enters a new range, you get the complete unknown. They're like, that's surprising. Fast radio bursts, dark energy.
The Boyajian stars, right? The things that are just truly unexpected. Even if the explanations turn out to be
dust,
quote unquote, boring. Even if it's just rocks and dust out there, things going bump and things moving in ways that you don't expect, or changing in ways that are just truly unexpected. As you said, every time we have a new data set and a new kind of telescope and a new kind of survey, and the optical and the infrared and the ultraviolet, whatever it is, any new frontier we push, we discover things that are just totally unexpected. And they might seem boring now in reflection, but they were mind-blowing when they were discovered. Yeah,
it was. I was talking to Pluto killer Mike Brown about his discoveries of all of those objects in the Kuiper Belt, all of these dwarf planets and stuff. And he's like, the Very Large Telescope came out, and we were able to see that much farther. We scanned the entire plane of the ecliptic. We found all these objects, and that's it. We can't find anything else until the next generation telescope comes along, gives us new capabilities, and we get to go to the next level. And those two really go hand in hand in lockstep. I want to shift gears now and
Sure.
talk about, I think, this is not your main job, but it's definitely a hobby, is that you're definitely involved in the thinking about the search for extraterrestrials, the possibility of technosignatures, the puzzle of the Fermi paradox. Let's talk about like some of your recent work in that field. What's like the most recent paper that you've been involved in?
The thing that I've been thinking a lot about for the last couple of years is, the two local expertise we have at the University of Washington. We have, I would say, arguably the best astrobiology institute in the world. We have this great team of interdisciplinary people thinking about other worlds and atmospheres and what Earth would be like around a young sun. And it's so exciting to see their predictions about what James Webb will discover. And then we have this team that I work with here in the Dirac group, thinking about big data, thinking about huge surveys, thinking about what can we extract from our technology and from these databases to discover the very rare comets and the very rare stars. And that connection between astrobiology and these big technologically sophisticated surveys is what's really drawing me into this search for what we call technosignatures. So the search for things for extraterrestrial intelligence or for the indications that there is technology out there changing things. So it doesn't have to be flying saucers, right? This could be patterns in our data that are just unphysical or unexplainable from natural phenomena.
And so what are some examples of technosignatures that have been proposed so far?
Yeah, there's a huge wealth, because even though this seems like the new frontier of science, this has been studied using mostly radio telescopes for like 60 plus years. So there's actually a lot of thinking that's gone into this, which is great. So we're not having to invent this entire field. Instead, we're just trying to adapt what's been done on the radio to these visible light surveys. So these are things like, I'm sure you and your channel have talked about this ad nauseum, but the thing like the Oumuamua, right? Things that are moving in perhaps unnatural directions. LSST will be the perfect platform to search for this, because it will discover thousands of comets, and you'll be able to trace them over time. And if they make a 90-degree turn, that would be a pretty big indication that something is unusual going on.
Yeah, boom. Take that, UFO hunters.
Right, there you go. Just go to the survey and wait.
Just wait for one object. That's I'm sorry. I just want to stop for 1 second. I never even thought about that, but you're exactly right. That you take this incredibly powerful telescope that is scanning the sky, and when the alien mothership stops,
right,
then that is like an asteroid or a comet cannot just stop in space in that way. But of course,
now it's a tricky regime, right? Because comets have these tails, they have these jets, and so they push them in seemingly unnatural directions. They do get these sort of non-Newtonian or non-Keplerian motions where they're not just orbiting the sun, they will take little jogs because they do have little jets pushing them. So, we need to work with the experts who study comets and also the people who study these databases to extract these objects. But I think that's a slam dunk project right there.
Yeah, but to watch this little blip move across the field of view night after night, go into orbit around Jupiter, like, boom, you're done.
Right. It would be a complete obvious signal.
Yeah.
There's a whole other class of really cool things out there that we can predict how do I say this? We can predict they shouldn't exist, right? So things disappearing is a great example. If you've got stars that are just doing nothing and then just drop out of existence, just disappear from view, this would be a big indication that something is, that they've closed the dome on the Dyson sphere, they've blocked out all the light. Now the thing should start radiating in the infrared at some point, because that heat's got to go from the star, has to go somewhere. But from our standpoint, it should basically just disappear. So that's a class of objects that should be very easy to write algorithms to search for, and very unlikely to exist. And then a whole project that I've been working on in the last month or so is what's called the SETI ellipsoid. So it's like a game of Marco Polo, if you ever played that in the swimming pool as a kid. Only we don't know what to look for or where we're looking. The idea is that if a triggering or a signal kind of event, like a supernova, goes off, and you observe it, then you would see that and you would yell Marco, or I guess you would yell Polo. I have to think about this. The analogy is a little fuzzy here.
We've never played it in Canada, so I have no idea how this game is
played. Perfect. Even better. This analogy is totally broken.
Yeah, that was great though, because I, as the alien civilization, have no clue what you're getting on about here.
Right. It's perfect. It's the perfect analogy then.
Yeah, it really is.
The idea being that you would see this event that would be noticeable everywhere in the galaxy, like a supernova or like some big novae. And it would go off, and then you would see it. So the light from that event would pass by you, and you would say, oh, look, my LSST has seen this nova go off. And I'm now going to flash my signal lamp, and let everybody else know that I've seen this. And so if you draw that picture of like the light rays coming to the alien star and then coming to us, then that forms an ellipse in the sky where you can say, based on that supernova we saw, this star over here would have seen it at, the speed of light is constant everywhere. Again, hopefully the laws of the universe are the same everywhere.
That would be.
And so you'd be able to figure out that, okay, that star over there is 10 light years away from us, and it's roughly the same distance from that supernova that we are. And so if they saw it, and then they blinked out their signal lamp saying, we saw it, we're over here, then that distance would be 10 years. That timing offset would be 10 years.
Right.
And so you can draw this like ellipse in the sky that is constantly growing. And you can use your surveys to be scanning the sky and be like, hey, we saw a star flare or something over here. And that happens to fall on this weird ellipse based on this supernova we saw, where if they had seen it, maybe that's them signaling us. Maybe that's them seeing the Marco and shouting the Polo.
Right. And so your thought is, with a telescope like Vera Rubin, in theory, you can look for these events that are linking up over the right periods of time.
Exactly. We don't know what it's going to look like. We don't know if a similar civilization has the capability of producing a pretend supernova. It might just be a small little flash of light. But if it's timed at just the right moment, that would have some meaning encoded, that we would be able to say, look, that star probably shouldn't have flared. Yeah. Or if it did, it's very unlikely it would have flared at this very moment that corresponds to when they should have seen that supernova.
Have you thought about what kinds of energies would be involved to actually send out a signal that would be detectable in a spherical pattern? I mean,
it's a ton of energy, right?
Okay.
Outshining your parent star turns out to be really hard. You can do it. We could do it with a laser, but only over a very narrow wavelength range. Producing light that's brighter than your parent star is really hard. So it turns out, energy-wise, blocking light is a little easier. You can throw up a giant star shade or a big piece of mylar and block out a lot more light than you can.
Oh, that's really interesting. I've never even thought about that. That's exactly right. That shining a light is way tougher than just blocking some light.
I mean, like, it's not trivial to block a light, right? Trying to create a Jupiter-sized mylar blanket to float in outer space is still like a catastrophically expensive project.
Of course.
But it's still a whole lot easier than producing a laser that produces optical light that's 1,000 times brighter than the sun.
I'm sort of imagining those like vertical blinds, and you would see the supernova, and then you would just, someone go out and turn the little thing and
blink, blink,
yeah,
blink.
Exactly.
Yeah, it's the signal blinds. Shutters, right?
Yeah,
on
exactly.
A ship or whatever.
Except you'd have to be able to do it in all directions. You've pretty much built a Dyson sphere. Like, isn't that just an elaborate excuse for building a Dyson sphere? Like, we need to be able to, the only way we're going to do that is to have a series of space stations in a complete sphere around the star. Okay.
Or a swarm of objects or something, right?
So that is, that, or even just like, let's assume that one of our alien neighbors knows that we're here. They decide they're going to shoot a laser directly at us to tell us, like, we see you. Hey, dummies, we just saw the supernova.
Right.
Are you paying any attention to us yet?
Right.
But let's say that they don't necessarily they're not broadcasting their existence. We are going to snoop on them. What sort of ways do we have that are possible?
Well, this is where like radio astronomy really has, I think, been the pioneer. Is that the idea that the best signals that you can look for are ones that are sort of inevitable. So things like waste heat, right? Like, thermodynamics says that you can't just like trap all the energy from a star. Your stuff is your Dyson sphere is going to get hot, and so it's going to radiate in the infrared. And so even if you're trapping all that energy from the parent star, we should be able to see you in the infrared. You can't hide at all wavelengths. So that's a good signal because it seems inevitable. If you do build this megastructure, even if you're not trying to be seen, it should be detectable. Another good example is like laser pulses. If you're using lasers to communicate with your probes or with your other space stations, seeing little flashes of laser light. We don't see stars flash like that in like nanosecond bursts. And so that's a good example. Those signals also encode a lot of our thinking about ourselves. We can only kind of imagine the sorts of technology that we have. And so it's very difficult to predict, like, what would a civilization that is far greater in extent and power than we are, what would be the inevitable signal that they would produce?
So let's sort of shift a little bit. I've talked to the astronomers I talked to who are sort of working in this field, you, Kipping, and others, Jason Wright. It feels like the more you think about this, the more the Fermi paradox is a really disturbing idea. It's really hard because, like, the more you start to think about it's not about the search, it's about the ability for alien robot factories to send spacecraft to every star system and produce more of them. And when you sort of look at it from that scale, or even their ability to build, go to every star and turn them all into Dyson spheres, what feel like inevitable, the inevitable outcome of continuous growth of the pursuit of energy, the evidence should be just plainly obvious that we are not alone in the universe, that there's some super weird reason that our planet hasn't been turned into a Dyson sphere yet, but the robots are on their way. How do you square that circle in your mind?
The first thing that gives me some comfort in this space is that, like, space travel is still catastrophically hard. And so we can definitely imagine that the civilizations that might be out there, would be able to build self-replicating Dyson sphere building robots and just send them out. And then, they just wait 100,000 years and they've conquered or they've spread themselves.
You just watch galaxy after galaxy shift into the infrared.
Right. But the number of assumptions there is just so huge. Like, we have no idea what the success rate of that kind of enterprise is.
Well, it just takes one.
It only takes one. That's right. But it's still increasingly hard the further out you go. So maybe. I'm also just really comforted by the fact that we've barely begun to search. And so obviously there are not alien spacecraft like Independence Day just sitting on top of us waiting to take us. There's the obvious signal that we haven't detected. But in terms of the amounts of signals that even we've considered, we've thought of, we've barely scratched the surface, right? We have, for the most part, done targeted radio studies of 1,000 or so nearby stars out of the 100 plus billion stars that are in this side of the galaxy. We've barely studied the sky. We've barely scratched the surface of the kinds of signals we can even imagine, let alone the ones that people will come up with. I think Jill Tarter said that it's like we've searched for life in the ocean. Mm-hmm. We're trying to find whales in the ocean. We've only searched one cup full of water so far. Like, we've searched this much of the ocean and we didn't discover whales. So
I mean, I know this is an interview, but I'm going to turn this briefly into a debate, which is, I just don't find that argument compelling because, she's Jill Tarter and, I think she's the greatest. So I'll have this conversation with you and not with her. I will just, thank her profusely for all of her work. But just this idea that it feels inevitable that we will attempt to send robotic spacecraft to other star systems, and it feels like we will attempt to make those robots build other robots and go to other robotic star systems, and alien civilizations will go like, what's with all these robots that have the word NASA printed on them that are all over the place? They just keep turning our buildings into robot factories. What's this about? NASA, V'ger. So, and so it feels to me like that is the inevitable outcome. Like, that's what we're going to do. Like, if nobody stops us, if nobody actually comes and breaks our robotic fingers, we're going to fill the universe with self-replicating robot probes.
And maybe,
sure,
maybe. If we find like an economic reason to do it, right? Like, this is the other like anthropic piece of it, is like, there's a lot of things we haven't done as a civilization on our own planet that we could do that are technologically very possible.
Well, and so that's the issue, right? Like it doesn't feel unreasonable to me that we will eventually be able to build a self-replicating robot factory for a few $1 million, and it'll off it goes. That and as long as you're patient, you just wait for stars to fly close to the solar system. wait 70,000 years and you can just hop from here to Gliese 582 or whatever. That, the trip time is actually shorter than you think. So anyway, it just kind of feels to me like you end up with two possibilities. Like we're either alone or it's impossible, that we will not be able to do that no matter how hard we try, because every civilization that's come before us has failed. And
I mean, I'm a little bit comforted by the latter answer. I hope the former is not true, that like it does seem like there's a staggering number of stars and that there are even more planets and that life should be out there. So the idea that we're alone, I mean, is definitely one solution. Like it's not ruled out at all by what we know about the frequency of planets and the occurrence of life, because we know precious little about how often life is produced on other planets.
Yeah.
But it is possible that we are the only life, or at least the only sentient life in the galaxy. But we may be teeming with life, and yet space flight and self-replicating robots that get to Proxima Centauri and get to Wolf 359 and all the other places, that may be impossible.
Yeah.
The good news about that, the part that gives me a little peace there, is that there may still be ways to at least, as you said, snoop on them, at least see them. I mean, you hear these statistics like if there is I'm going to misquote this, but if there is an airport within like 50 light years, ALMA could hear it.
Yeah, 100 light years.
I mean, right? Like that's an amazing.
The square kilometer array can detect an airport, can detect the world's air traffic within about 100 light years.
So that's amazing. Okay, there's probably not any other airplanes within 100 light years. It's not that big of a bubble. Although there are like 200,000 stars that you could possibly look at within 100 light years. But no, 100 parsecs.
No, there's 1,000.
Yeah,
1,000.
Yeah, 100 parsecs. There's a couple 100,000
stars.
So if you get a factor of 3 out even further,
yeah,
then you start to increase your sample. And anyways, I'm comforted by the fact that maybe space flight is hard, and we're never going to get the Star Trek future that I grew up wanting, to fly between the stars.
I'm not listening.
Like maybe,
that is
but
impossible.
It doesn't mean we're alone, right? It doesn't mean that like the most profound questions about whether or not we're alone and where we come from, and you can extrapolate that into even more profound questions about what the purpose of life is, perhaps.
Yeah.
We still, I think, can look for them. This is what excites me about this, is that we don't know. And we're building these surveys, we're building this technology to look for things that we do know is out there. Kilonova and supernova and eclipsing stars and exoplanets. We're building the technology to find these things. And so the calling that I'm feeling at this point in my career is we ought to look.
Yeah.
I don't know all the possible signals and lighthouses and beacons that might be out there. I hope that people like you, I hope people like David Kipping and Jason Wright and Jill Tarter and all the rest keep coming up with these great ideas of ways that we might look, because why not look? Yeah. What else is the point?
Well, I mean, for me, it's really about, like, if we are alone, then life formed in one place in the entire Milky Way, and we wrecked it. We screwed it up. And, right? That it was, on our watch, here was this great opportunity to seed a universe with life. Life is better than non-life. The universe is made better with all the diversity of life that Earth can provide. And the universe said, okay, humanity, do your job. And we're like, we're just going to fill the atmosphere with greenhouse gases and fill our oceans with plastic and run out of usable energy and then leave nothing for the dolphins or the whatever comes next, and because we used all the readily usable material. So anyway, I feel like,
I mean, look, dinosaurs were here. Dinosaurs were massively complicated, humongous animals, and they lived for a very long time. And as far as we know, they didn't build any radio telescopes.
No, they blew it.
They had their chance.
Yeah, exactly. So it feels to me like
life may be very common.
Yeah,
life may be very common.
But
there could be dinosaurs everywhere.
If we did find life on another star system, I'd just be super relieved. I'd just be like, oh, the pressure's off. Like now, right? Like now it's not our job. Now somebody else can just be building that galactic civilization, or even just making sure that life exists beyond the moment where our sun bloats up and cooks the planet.
I mean, what we can say with certainty is that life must be precious. We don't see aliens just walking by. So it's either super hard to get out there, and or life is rare.
Yeah.
I think that puts a value on on what we're doing.
Yeah,
I
well
think
said.
that puts
Yeah.
environmental value on what we're doing, and that's important.
Yeah. So I've got some, I want to get some questions from the audience. If you want to talk about some of these ideas of searching for life, if you want to talk about time domain astronomy, if you want to talk about the nastiness of red dwarfs, being a astronomy YouTuber, any of that, definitely post some questions. I've got a couple here that have already come through, so I wouldn't mind throwing them your way.
Are you going to read them to me?
Yeah.
Perfect.
I always hide my window in the wrong place. Okay. So Arjun asks, will we in the near future be able to detect how long a planet would be habitable?
Maybe. I think we'll know that answer. I mean, we're going to have that answer statistically. We're not going to ever watch a single planet for any appreciable amount of its life, because I'm not going to live that long. I won't live 100 million years to watch what happens to the orbit or the evolution. So it's going to be a statistics argument. Will we be able to see enough planets around stars with different stages of development? And I think the answer is yes. We've already seen planets around really young stars, hot Jupiters that are really close in, planets around stars like Proxima Centauri, which are very active and potentially very inhospitable. So I think so. Yeah, I think the answer will be we'll have enough. We have like 4,000 known planets. That's a ton.
Yeah.
We're going to see in the next few years that number continue to grow rapidly. When you have 100,000 planets, we'll be able to pick and choose and be able to map that evolution from young to old, from massive stars to low mass stars. Mm-hmm. And that's again where the statistics and the algorithms are going to be really helpful.
It is interesting that in the olden days we counted planets on both hands, and now we're into the thousands. We're shortly going to hit into the tens of thousands. I saw one estimate that puts us in the tens of millions by the mid-century. That it shifts from each planet being its own unique snowflake to each, that you're looking at millions of planets at a time and considering them in a vast mathematical approach.
I'm glad I was not in the planet hunting business 10 years ago, because it was super competitive. Like,
I
people
do
were
not
super
want to have
guarded.
to hear about, planet Peg 51 again.
I mean, people were like guarding their data.
Yeah.
And, you would write a paper on a single planet. And, that still happens, but it's very rare now. Now we get these catalogs of like, here's 100 more, here's 1,000 more.
I can remember like the moment when I saw a press release for a planet. I was looking through Archive and it was like, 2 new planets discovered at this. I'm like, 2? I've seen more. Next. Next. Yeah. Let's move on. I think we can do better. Come back when you got like 4.
But what's great, right, is when you start to have huge catalogs where the discovery of a single planet amazingly, right? It's like going to the moon. When that becomes boring, then you start to wonder what's rare, right? And this is where people start discovering the very unique planets. So, right, we have a precious handful of planets that have been discovered in very strange orbits, or planets around binary stars, or really unique configurations that challenge our understanding of formation and evolution of planets. You only get those things when you start having big catalogs. So, I predict, my prediction for you, Fraser, is you'll still be having a lot of press about single objects. But those superlative objects will only appear once we have 100,000 of them.
And that's going to be exciting. I mean, people always ask me like, where would you like to go in the universe? Where would you like to go in the Milky Way? I'm like, I don't know. Like, nobody's done a good job of surveying yet. I can't make that choice. Right? I need someone to deliver the goods. Tell me about a world that has 3 stars, and we know that it has, vast oceans and a forested moon. Now we're talking. But
Gaia has only mapped like 2 billion stars out of a few hundred billion, right? We haven't even mapped 1%.
Bozo asks, ask him what's been ruled out in terms of ET. It's Bo Space Zo. Not
Bozo.
Yeah, Bozo.
What's ruled out? Again, I think it's actually very little. It is the very obvious. We know there are not. We know there are not very large star destroyers flying right next to us. We do have actual good maps of the sky every night or two. We do map between ZTF and TESS and the surveys that do Assassin, the surveys that do exist. We can rule out big things moving through the solar system. Things like Oumuamua are pretty small. So we can rule out big things. That's good. or maybe that's disappointing. I don't know. That's good. We can definitely rule out a lot of radio signal from a lot of the nearby stars. So the Breakthrough Group, for example, has been doing a really methodical job of surveying a ton of nearby stars with radio telescopes. So there is a lot of like radio signal that we can rule out. And then from the standpoint of like the optical surveys, well, okay, we've only found one Boyajian star-like object, but there is a ton of variability, sort of flickering and dimming and things of stars that maybe are not as dramatic as Boyajian star, but there's a lot of stars that have had that kind of behavior that we don't quite understand. And there's a lot about the potential of building Dyson spheres that we have not been able to rule out. The disappearing stars, there's been a few candidates of those. Most of those either have had dust or some other explanation. There have been some sort of nova. So we can rule out any of those from the nearby stars. But as soon as LSST starts churning out data, this search will begin again for even fainter things. So I feel like the field of play is pretty open.
Yeah. But it is like, as those powerful new observatories do come online, as you get things like James Webb or Voir that are capable of detecting exoplanet atmospheres, that you will start to be able to rule them out and go, nope, nothing there, and you're looking out as far as you can detect, and it's all just something bland.
Yep, that's right. And I think that's important, right? Being able to rule things out is important. That's what makes this science, right? It's
right.
We can go look for things that perplex us, but we have to be able to explain what we see. And so any candidate we find, we're going to hit it with everything else we have to try to show that it's just boring dust and rule anything else out. And that's part of the work.
Well, we're sort of nearing the end of the hour that we set aside to chat. It's been great. But James, if people want to, I guess, what are you working on right now that if people want to sort of follow your latest adventure?
Yeah, right now my efforts are split. Right now I'm working on understanding stars with the TESS survey. So we're studying flares. We're studying what we call magnetic activity, which the sun produces, but thankfully not much of. So we have a habitable place, a comfortable place to live. We're studying these very violent, very outbursty stars with TESS. So we've got a lot of work going on with flares and star spots and things like that. So I'm excited about studying those kinds of things with the TESS survey, which is flying right now. And a lot of the work that I'm developing and grants that I'm writing right now are on technosignature searches with missions like LSST or the ZTF program.
That's really cool.
So that's what I'm hoping to work on. And hopefully I'll be on YouTube as well, sharing some of that science.
Yeah. Are those kinds of grants actually getting picked up these days? Are you finding that I want to look for aliens, or people are going, yeah, okay, sure, have some money?
It has been difficult, I will say. It has been difficult right now. So there has been sort of a moratorium on funding this stuff. Now there is language in the grant calls that say we're open to it.
Yeah.
So we're writing, not just me, but myself and others are writing proposals as feelers. And so I think this proposal I'm working on right now, this is a feeler. It may get shot down for not being the most exciting science, but I would love the chance to actually get it reviewed. That's a big goal for me.
Yeah. I think it's great. Definitely you can feel that sea change that's going on from.
I think so.
And I think there's been a lot of people like you, David Kipping, Jason Wright, even especially Avi Loeb, like a lot of researchers who, and then of course as I said, Jill Tarter, Seth Shostak, people who have focused their energy, but had to be sort of outside of the traditional funding set for the longest time. Now,
I think it's a great time to be doing SETI work, technosignature work as your 10% of your research portfolio. That was what Jason Wright's suggestion was to me. Like, do it as a side part of your work, because the byproduct of looking for the extreme or the rare is that you discover really amazing stars, or the byproduct of looking for aliens. Okay, you might not find aliens, but you might get a Nature paper or a really prestigious publication because you've discovered something incredibly rare. The byproduct is really good science. It's not a waste of time.
And what is the best place to follow what you're doing?
I spend too much time on Twitter. That's a great place to interact with me.
Yeah.
You see?
Yeah. Judging you harshly. But only a person who spends too much time on Twitter would know that.
Yeah.
So, yeah.
Yeah. Only somebody who's replying to me in the middle of the night would know that. And then my YouTube channel, which has been a great place and a great community for me to reach out to people. So it's youtube.com/James_Davenport. I forget.
And I'll put a link. I'll put a little Cardi Blops in front, and so it'll link.
But I'm trying to produce a weekly video there. I'll get back to that once the pandemic recedes some. And the goal there is to share what it's like to be a scientist.
Yeah.
It's about the people and the experience of being, so I do talk about science, but I also talk about just the daily life and the work and the travel and the grind.
Yeah, and I think that's great. And I think that's really appreciated by the people who are in the field, just who wished someone would take the time to explain how you do your job. And I know as well, for me, being able to sort of get a sense of what your work, you're like another set of eyes at these conferences that I'm not seeing the stuff that you're seeing, and then I can sort of follow up. So it's it's great work. I really enjoy your YouTube work. So thank you so much. Yeah, man. All right. Well, I hope you can continue to hold out for the rest of this this pandemic without continuing with all the papers, and I hope that we'll be able to hang out in person at an upcoming AAS meeting.
I'm optimistic. We'll see each other soon, I'm sure.
All right, man. Take care. Thank you.
Thanks, Fraser.
Find the